Welcome to Lecture 4.3. In this video, I'll be covering what I like to call the post-EAS modification reactions. Using the EAS reactions we learned last time, we have access to some of these benzene derivatives that I want to now give names to. So one group is the R group, right? We can use this is a methyl group specifically, and we could make this chemical by using the Friedel-Crafts alkylation. Now, we call this toluene specifically when there's a methyl group there. It's good to know that in terms of naming. There are some groups that are just hard to know in terms of, like, for example, nitrobenzene isn't that difficult. There's a nitro group on the benzene. Same with bromobenzene. Same with sulfobenzene. But things like toluene might require a little bit more effort on the side of memorization. Another example of that is acetophenone, when you have a ketone with a methyl group or an acetyl group on your benzene. We have these derivatives, and that's awesome. But we can generate many others by further reacting these EAS products. These reactions are not going to be EAS reactions anymore, because remember, EAS reactions specifically involve the three steps of activating an electrophile, benzene attacking, and then aromaticity being restored. So unless benzene is attacking, unless we're adding things directly to benzene, it wouldn't be an EAS reaction. Now, what kind of reactions am I talking about? Let's look at a couple examples. From toluene, we have two different options that are usually covered in my experience. The first is we can use radical halogenation. So using Br, or Br2, so bromine, and some sort of UV light source or heat, right? There are other ways to do radical bromination. Other professors may have different conditions that you need to know. But what this will allow you to do is actually replace one of these hydrogens, right? Remember that a toluene will have three hydrogens up here. It'll allow you to replace one with a bromine. Right, so now, before we had these alkyl groups, now we have alkyl halides. Right? We may have trouble adding this directly, but we can use this method. A more useful one that gives us a functional group that we couldn't otherwise have is the use of potassium permanganate, which is KMnO4. We'll talk about KMnO4 again soon in the oxidation reactions, but briefly, what it's going to allow you to do, it's a very strong oxidation, or very strong oxidizer. It's going to cause a lot of oxygen to join the molecule. And what this does is it converts that methyl group into a carboxylic acid. Now, a carboxylic acid is not an acyl group. We cannot use the Friedel-Crafts acylation to make a carboxylic acid on the molecule, which means that we can't do this directly from benzene. However, by knowing about potassium permanganate, we now have a two-step way to make that carboxylic acid. The name of this, by the way, is benzoic acid. Right? What we have to do first is use FeBr3 and methyl bromide. This is the Friedel-Crafts alkylation, which will allow us to add an alkyl group. That will be the group that we use to make benzoic acid. Cool. That's from toluene. What about from nitrobenzene? There's one important reaction I want you to know, and that is the use of a reaction called the clemmensen. We'll see this reaction again, doing a different role, but it has the very useful property. Okay, the clemmensen uses zinc mercury amalgam in the presence of HCl aqueous. So hydrochloric acid, very acidic, very dangerous and strong conditions in the presence of this mixture of metals. And what that does is it actually replaces the oxygens in this molecule, connected to that nitrogen, with two hydrogens. This is now referred to as aniline. Right? Nitrobenzene has turned into aniline now. Right? That's an amine. Again, we don't have a way of adding amines directly to benzene, but from benzene, I can use HNO3 and sulfuric acid to add that nitro group. Then, subsequently, apply the clemmensen reaction to reduce it down to the amine or form aniline. Great. So not only do we have the five listed above, we also can make carboxylic acids, and we can also make amines. Right? Previously, benzenes were this difficult thing to react with, and now it seems like we have lots of different options with them. Lastly, I wanted to quickly cover acetophenone as the second use of the clemmensen. as one thing you can do with carbonyls is use the same clemmensen reagents, that's the zinc-mercury amalgam with HCl, and in the previous reaction it replaced oxygens with hydrogens. It's going to do the same thing here. What this allows us to do is basically, it looks like remove a carbonyl. One thing I like to say is if it was a Harry Potter spell, it would be Cotonus deletus, right? It's just gone. But in reality, we've actually replaced it with 2 hydrogens. This is a very, very useful idea that we're going to revisit in video 4.5 to help us solve a problem. Before we do that, though, I want to make note that I understand that I've basically just shoved a lot of reactions down your throat at once. We have 5 EAS reactions with all their conditions. We have, 3 new reactions in terms of what modifications can happen after. And a key problem a lot of students have is, well, how do I effectively study this? In the next video, I'm going to give you what I think is probably the most effective value that I can give you, a study method that I refer to as the ABC method, that will help you really be able to remember and understand these chemicals. I'll see you in video 4.4 to cover that.